Hello everyone, this is Subrat Roy. Today in the International Web Conference on Advanced Research in Science, Humanities and Social Science, we give a little more explanation about our work. This work done jointly by Mr. Subrat Roy and Dr. Shantanu Raut. The title of the paper is Dynamical Analysis of the Force KdV equation by the Multiple Scale Method. Nonlinear phenomena play a fundamental role in applied mathematics and physics. Recently, the study of nonlinear partial differential equations in modeling physical phenomena has become an important tool. Fundamental exact solutions of nonlinear evolution equations has become one of the most exciting and extremely active areas of research investigation. A variety of powerful methods have been presented, such as inverse scattering transform, Hirata's bilinear method, sine cosine method, homotopy perturbation method, homotopy analysis method, etc. Computational mathematics and symbolic programming have heightened the evolution of solving nonlinear problems, and it has become easier to handle and rearrange the sophisticated mathematical equations. Most of the complicated nonlinear partial differential equations were solved by numerical analysis and asymptotic perturbation techniques. Recently, many researchers have solved the classic form of force KdV equation by numerical methods and approximated analytical methods. An analytical model of tsunami propagation was proposed by Pelinovsky et al. FKdV is an alternative approach is describing the governing equations for the basic hydrodynamic model of tsunami generation. The forcing term in the FKdV can be assumed to be derivable from atmospheric disturbances. Also, the forcing term plays important role to make various structure of the system framed by the form of FKdV equation. In the recent paper, the above mentioned considerations motivate us to investigate the approximate analytical solutions and analyze the dynamical behavior of the force KdV equation by using the method of multiple scales. The method of multiple scales is often used in the analysis of weakly nonlinear dynamic systems. These models from the perturbation techniques are chosen to perform the analytical analysis of a base excited hardening nonlinear system. A few perturbation techniques are available for solving the nonlinear oscillations and that involve the straightforward expansion, the Lin state Poincare method, the multiple scales method and the averaging method. All these perturbation techniques have been applied by many researchers in analyzing nonlinear oscillatory system. Our aim of this article is to applying the multiple scale method to obtain approximate analytical solutions of the KdV equation with forcing term and analyze the dynamical behavior by constructing limit cycles. Here I consider the nonlinear KdV equation of the form. Now introducing the transformation t equal to x plus theta, we have the equation 2. Now we select the force KdV equation in the form 2 and 3. Now integrating we get equation 4 where k is 1 is the integrating constant. Finally, applying the parameters we get the equation 6. Now using the method of multiple scales, the solution of this equation can be written as, here epsilon is the parameter which is less than 1. Using different time scales t0, t1 and t2 and equation 7 in equation 6 separating the terms with different order of epsilon, one can write the following equations. Now the solution of the one order equation is of the form, here a is the unknown complex function. Now substituting this solution into epsilon order equation leads to the result. To have a bounded solution, one should eliminate the singular term and hence therefore a must be independent of t1. So the previous equation can be rewritten as The particular solution of this equation is now using this value and the value of u0 into epsilon square equation, we have the equation 14. Now, to eliminate the circular term, coefficient of ipt0 e to the power ipt0 should be equated to 0. Hence, we have equation 15. Now, using a equal to a by 2 e to the power I gamma, where a and gamma are real function of T2. This using into equation 15 and separating the real part and imaginary part, one obtains. Therefore, we have the solution. Finally, we get the solution of the fourth KdV equation. Now, from the above calculation, we see that the periodic behavior of the solution, taking the values of different parameters, the time response has been plotted. Graph of displacement versus time is presented for multiple scales. Also, it is noted that the response of the system increases linearly. Here we draw the limit cycle of period 2 for different parameters. We depict the 3 periodic limit cycle for different parameters. We plot a multiple periodic limit cycle for different parameters. Here we also draw the multiple periodic limit cycles. So, here we see that the system maintains a single periodic limit cycle to for f lesser or equal to 0.2. If f belongs to 0.2 to 1.5, the system follows in general 2 periodic limit cycle. For multiple limit cycle, f should be greater than 1.5. However, effects of omega significantly changes the structure. Our investigation demonstrates that the external force plays important role to make different structure of the system. It is evident that as f increases, the system grows from single periodicity to multiple periodicity. When f very large, the system may go in a chaotic structure. The detailed dynamic study for the present observation will be analyzed in a subsequent literature very shortly. Thank you.